Welcome everybody. Welcome everybody. It's my pleasure to welcome Martin Lotz to the 1W-MINDS seminar. Martin studied at ETH Zurich and then he did his PhD at the University of Paderborn, and then he started to go all over the globe. So he's been to Hong Kong, and then he came back to Europe, and he's been all over the UK. So I think he's been to Oxford, then Edinburgh, then Manchester, and now he's an associate professor at the University of Warwick. And scientifically, Martin gets around a lot as well. So he's sort of a Renaissance man who has contributed to many, many fields like topology, computational geometry, computational complexity. That's his origin. And he will even go into dermatology if you ask him nicely. And it's our pleasure to have him give a talk on concentration of measure in geometric probability.
Okay, so thank you very much, Karen, for the introduction. So today's talk will be, say, slightly on more on the pure mathematical side. So it will talk about a certain approach to geometric probability or integral geometry, which is a very classic area in mathematics, dating back to more than 100 years ago, or maybe 200 years ago. And this kind of, but the problems that we look at, so the motivation to look at the problems the way I will be looking at came from applications, and that came from different areas. So I will start with talking a little bit about where the questions came from that we have been asking, and then how we decided to tackle these questions. Okay, so as I mentioned, we start with a motivation. And so first of all, so we start with a very basic problem or say a very fundamental problem in geometric probability, probably so the problem that started this field more or less in the 18th century. So Buffon asked about the probability that if you throw some needles, or actually in this paper he called them baguettes, so that's why I illustrated it in this way. So if you throw them on a plank 4, what is the probability that they will cross so certain lines, or that they will touch 2 of the planks? And so an elegant solution was then given in the 19th century. Oh, by the way, I'm really bad at including references in this talk, since I adapted this from a handwritten talk. So so in many cases I probably should have cited a lot more than I will be doing in this talk. So I can point you to more references if you're interested later on. Well, in any case, this problem has been solved so quite easily. So you can kind of give an exact probability. Say if the needle has a certain length d and the planks have a width of, the length is L and the planks have a width d, then so you can compute the exact solution. So the case where the length is smaller than d, there's this kind of so it's a rather famous trick, so called the Buffon's noodle. So with which you can compute this probability, but you can also derive an exact formula so in terms of d and L in the case where the length is greater than d. But in say going beyond these exact formulas, like in mathematics, quite often you can tell things about a problem or about the solution of a problem without actually solving it. Like a typical example would be, say, differential equations, where you can derive properties of the solution without actually solving it. So in this case, you can certainly make statements about the, say, like saying that if the length of the needle is very small, then the probability will be almost 0, and if the length of the needle is very large, then the probability will be almost 1. So fitting the boundary. So this is generally a different kind of statement that you could, in principle, derive, or you could say something useful about the probability that you're interested in without actually having to calculate it exactly. Okay, and so so I started with this motivation from a purely mathematical problem, but the same kind of considerations also appear in problems that arise from applications. So I will go back a little bit to some work that I've been doing now almost 10 years ago. And so this was related to what's roughly or broadly being seen as compressed sensing. So you try to, again, in the simple case, so you try to make certain observations. So you try to make measurements of a signal, but sometimes the number of measurements that you have are less than the dimension of the signal. But you still try to recover the signal from that, and it turns out, so this is the classical theory of compressed sensing, like that in many cases, if X has a simple structure, it's a compressible or a sparse signal. So this is the theory of Candes-Tau and Delson, Bershinin, and others. Then and Donohoe. Then so you can actually recover this signal using optimization, even in the underdetermined case. So when you have less observations than what the dimension of the signal is. And so the way you go about this is you simply minimize a convex function. So it's in the simple case where we have exact equality here. So you would simply minimize a convex function subject to the constraints AX is equal to B. And in some cases, say you would take the one norm if you want to recover a sparse signal, or you can also take other norms if you want to recover some other types of structure. But the main reason why this works, at least in this exact case, is that due to there's a geometric condition that tells you when this works. And so essentially this works if so you kind of recover your solution X naught if and only if a certain optimality condition is being satisfied, say that the kernel of A intersects the cone of descent directions of our function f at our signal X naught only at the origin. Okay, so this is a geometric condition, and so the descent cone is defined formally simply as the set of the directions in which the function decreases. And now, so the toy problem that has been looked at early on in the game in this setting here was that you would take A to be Gaussian. You could also then, so later was generalized to other regimes. But in the case where A is Gaussian, then the kernel of A would be uniform distributed in the set of all subspaces of the according dimension. Okay, so this is the basic geometric problem, and then you kind of ask, so what happens if A is random? So what is the probability that random subspace intersects a cone? So this is so again a classic problem in the spirit of geometric probability. So you have, say, random geometric objects, and you ask. So of course, I mean, the problem becomes more complicated if you don't have exact equality, X is equal to B, and then so the problem becomes a different one. But in this basic setting, it becomes a problem in geometric probability, and this also means that so just like with the Buffon's noodle problem or with other problems that I'll mention later, so you can, in principle, get an exact formula for the probability that you're looking at. So you can simply write it down exactly. And so if we translate this problem now from the application that we started with into a purely geometric problem, so the setting is that we have a closed convex cone, say the cone of descent directions, or dually the subdifferential cone of f, but we'll not go into this. And so you have a certain linear subspace, and you ask, so what is the probability that this subspace intersects the cone non-trivially? And so formally, so you would kind of have to define a measure on the Grassmannian on the set of subspaces of a certain dimension. But so I'm not going to the details there, but so simply think of, say, the kernel or the image of a Gaussian matrix. So something that's uniform, right? So where every position is just as likely as any other. So I think that's the important point here. And so the exact expression for this is that, say there's a formula that's called the Crofton formula, and it can be expressed in this way. So this is one of the forms in which you can express it. So you can say that the probability that, say, if you take L uniformly on the Grassmannian of D minus M planes in RD, then the probability that this random L intersects the cone, say you have your cone, you spin around your space, the probability that it intersects is exactly given as the sum of certain invariants of C, which are called the intrinsic volumes, or the spherical intrinsic volumes in this case, which is a notion that was defined by McMullen in the 70s. Well, the term was coined by McMullen, but it's related to older quantities like the Quermass integrals that have been studied earlier by Santalo, Blaschke, and other people working in geometric probability. And I get more into this. But so for the moment, the thing to keep in mind is that we have exact formulas for the probabilities that we want in terms of certain geometric invariants. And really all we have to do is simply, if you give me a cone, so if I can compute these quantities, I know the exact probabilities, right? And in principle, so essentially this is what was kind of done. Well, so the problem is that these quantities are in general not easily computable. This was done in the case of the descent cone of L1 minimization. So essentially some early work by Donohoe and Tanner amounted to computing asymptotics of these quantities and estimating them. So that was and that's something that's highly non-trivial. Okay. So while we do have exact formulas, like in the example before, these might not be very useful. So we can even generalize the problem. So we can look at two cones, and I just randomly spin one. So I take one cone and it spins around randomly, and the question is, what's the probability that it will intersect the other cone? And again, so we can express this as an exact formula in terms of these invariants that are associated to these two cones. And so if you look at this, essentially well, the one thing that I should mention about these invariants, about these intrinsic volumes, is that in the case of cones, in this setting, so these are called spherical intrinsic volumes, they are non-negative and they sum up to 1. So they form a probability distribution, essentially, associated to a cone. Okay, and this kind of suggests that so maybe one can simplify these formulas here in some way. And of course, so one can define. So first of all, one can plot these intrinsic volumes for various cones. So this would be the circular cone. So this would be a cone or spanned by a spherical cap of say radius pi divided by 4. So it looks like this. But you can plot this for all kinds of other cones, polyhedral cones, whichever. And then so you can define a random variable associated to a convex cone, and then say that the probability that this random variable will take the value k is given by vk. Okay. See, and then of course you can define the expectation, right? And so it actually turns out that this expectation so it turns out to be equal then to the squared Gaussian width of the cone. So for those coming from a background in geometric functional analysis, but we'll not go into this. So the point here is that we have this probabilistic interpretation of these geometric quantities, and then so if you plot a few examples of what they look like, so they look like they form a like they might concentrate. So if you take the same cone and you look at very high dimensions, so it kind of looks like so it also looks like if these quantities would be log concave or unimodular, but this seems to be an open conjecture as far as I know. So no one seems to be able to. Yeah, that's something. So I don't know if so I believe it is not known where they form a log concave function. But so in any case, so we have these quantities, But then, so the point is, so we can actually show, and this was some rather old work that, well, old, 8 years maybe, so that we did. So we simply, so what we showed is that these, this random variable here, so concentrates around its expectation, right? So the probability that x deviates from delta c by more than lambda is bounded exponentially. So in in this way, and so what this implies. So if we go back to these formulas here, so this implies that, well, so the sum that we have down here, so it looks like approximately like a tail of this probability distribution. So this will be something that will then be either 0 or 1, and the same here. So we can expect this probability to be either close to 0 or close to 1, and the same here. So this actually looks almost like a, so you sum only over the odd terms, but you have the factor of 2, but using some interleaving property, so you can show them that this quantity will be close to 1 or close to 0, depending on whether the dimension m is larger or smaller than some certain threshold. So you kind of can use this result to obtain, yeah, like we said here. So you can kind of use this concentration of the intrinsic volumes to simplify and obtain approximate versions of these Crofton and kinematic formulas that I just mentioned. That instance, you simply replace this exact probability, so with something that depends only on one parameter rather than on the n parameters. You simply take the summary parameter, the mean of these intrinsic volumes. So instead of taking all of them, and essentially the yeah, here's a kind of illustration of what happens if you apply the kinematic formula. So you have the exact, so you have, say you take two cones, you take the non-negative orthant and a circular cone, and these are their profiles, these are the intrinsic volumes, and then so you compute the kind of like a convolution of these, and then from this you can kind of read off the probability that they will intersect non-trivially. And if you change the parameters of one of the cones, then this profile changes. So the mean is now here, and the probability that they will intersect. So roughly speaking, what you have here is that you, so for example, here you have the orthant and a very thin circular cone, and the probability that they will intersect randomly is almost 0, or it's very small. Now, if you take a very thick circular cone and the orthant, then the probability that they will intersect is very large. So you kind of, in these examples, so I calculated the probability by taking the convolution of the intrinsic volumes, because for these examples, we know how to compute them. But in general, you can make the same kind of statements without actually having to compute them. And this is, say, the approximate versions of these theorems that follow. So if you take a uniform subspace, and then so the probability that that the intersection will be empty with a cone is either greater than 1 or minus this eta, or it's smaller than eta. So depending on whether the summary parameter, the expected value, is smaller than m minus something or bigger than m minus something. And I should add that these approximate versions, they coincide with the versions that have been derived using Gordon's escape through the mesh argument, which comes from a different direction, which looks at, say, the kernel of a Gaussian matrix. Okay, so you have this, so the same with the kinematic formula. If you have two cones, and so you take a random rotation of one cone, and you ask for the intersection probability with the other cone, then you kind of get the same kind of statement. So you get that if the sum of these dimension parameters is smaller than d by a little bit, then they will not intersect with very high probability. If the sum of these expected values is slightly larger than d, then they will almost surely, well, not almost surely, but so they will with high probability intersect. So kind of these parameters kind of behave also a little bit like a notion of dimension. Like if you have linear subspaces, where the dimension add up to more than the ambient dimension, then they will intersect. If the dimension adds up to less than the ambient dimension, they will not intersect. So here you have a kind of like a probabilistic version of that. And so one way to derive this is simply by taking the exact formulas and then showing that the quantities that appear there, they satisfy some concentration of measure. Okay. And so of course these interpretations, so these applications here, they translate, say, if you translate them to the setting of descent cones of a convex function that you try to minimize, so you kind of get these kind of phase transition results. Okay, so you try to find a structured solution of a system of equations by minimizing a convex function subject to ax equals b, and then the result is, well, if the kernel of A intersects the descent cone, then this doesn't work. If the kernel of A does not intersect the descent cone, then this does work. And now if you simply take the results before by replacing C with the descent cone and L with the kernel of A, then this translates to these kind of results, right? So if the number of measurements M is slightly larger than this dimension parameter, then you have success with high probability. If it's smaller, you have success with small probability. And again, this is from the previous paper. So if you plot this, say for different cases like the one norm, then so this is kind of sharp. Okay. Now, so the point here is that while in previous work on say the probabilistic analysis for optimization problems, we had been working with the exact formulas and trying to compute these intrinsic volumes. So the point here is that what has been of interest in applications is more these kind of statements like in a certain regime something happens with very high probability, in another regime something happens with very low probability, and you can kind of transform these exact statements into these approximate statements by so using certain concentration of measure tools. Okay, now this was one motivation. So different problem that so we have been looking at. I mean, this also kind of like a bit of a toy problem is if you say essentially you can also use these kind of things to study randomized algorithms, right? So if you have some kind of, so you try to minimize a function over a convex set, and then you intersect with a random subspace, and then you search along the subspace, and then so you can also formulate an analysis of this kind of problem in terms of these intrinsic volumes, but then also use the concentration of these. Okay, so this is now mostly motivation. So this was problems related to cones, but the idea of intrinsic volumes is much older, and they were classically defined for convex sets in Euclidean space, not for convex cones. And these quantities are much better known in mathematics. So I will give a brief survey of the Euclidean integral geometry now. And so the starting point for this was really that this was Steiner in the 19th century. He well, so first of all, it's easy to notice in 3 dimensions or in 2 dimensions even. So say if you have a like this triangle, right, and then you can see that the area, say if you enlarge your triangle, say you add some lambda neighborhood to it, then the area of the whole thing will be the area of the essentially the area of the triangle plus the width times the circumference. Let's say the lambda times the circumference plus the area of a circle. Right, so this is simply if you subdivide this into these rectangles here, and these together make a circle. And in general, so what you see here is that then the area of this lambda neighborhood is a polynomial in lambda. And this is like the very simplest case of a general principle, which is the Steiner formula, which tells that in higher dimensions, if I enlarge, so if I take the lambda neighborhood of a convex body, then the volume of that will be given by a polynomial in lambda, and the coefficients are up to some constants here. So these kappa here are the volumes of K balls. So these quantities here, they turn out to be intrinsic, so independent of the embedding dimension. So if I take my convex body and plug it into a higher dimensional space, these will not change. And these have been also coined intrinsic volumes by McMahon. So they're closely related to, again, to a lot of quantities that appear in differential geometry, like in, say, certain curvature invariants. That so there's a famous formula by Weil on the volume of tubular neighborhoods of manifolds, and so these quantities are closely related to that, and they don't only work for polyhedral sets. I mean, this example that I was drawing here was for polyhedral sets, but they work in general. And even though in case of smooth boundaries, you can express them in terms of curvature integrals. And these are very classic notions that have been studied quite a lot, and they satisfy a lot of properties. So these are invariants. First of all, if your convex body has dimension m, then there are m of them that are non-zero. And they're monotone, so they increase if you have one convex body included in another one, then they get larger. They're homogeneous, so they're kind of like generalized volumes. And so in a way, you can also get them from as a special case of mixed volumes, say of convex bodies. And so they also satisfy a property that I did not mention here, but this is the property that they are form a log concave sequence. So they're invariant on the rigid motions. So if you move your body around, they don't change. And they're intrinsic. This is what I mentioned before, and they form a certain valuation. So we'll not need this property, just including this for completeness, and they're also continuous in the Hausdorff metric. But the point is that they tell you something about your set. So you have your convex set. They tell you something about this, and these quantities also appear in problems in geometric probability. So before I come to the applications of these, let me just briefly mention two examples. Say if you have a parallel top R with side lengths lambda 1 to lambda n. So a special case would be a cube, for example, in the case of a cube. Say in the case of a unit cube with side lengths 1. This should be lambda I, right? And then you have 2 to the n. And these EI are the elementary symmetric functions here, right? Or in the case of a sphere, you can also write this down exactly. But these are more or less essentially what you can also get expressions for zonotopes or for the projections of cubes. But these are essentially the cases where we kind of closed form expressions. So for these intrinsic volumes, so in general, it's not very easy to say given a body to figure out what the intrinsic volumes are of these. Okay, and so now we start with the kind of applications of this, or applications to geometry at least. So not applications to, so in the sense of real world applications. So here, so one would be a characterization of the nth intrinsic volume, say as the average volume of a projection onto an n-dimensional subspace, right? So I can take my convex body and then I can look at all possible projection directions. So I can all possible ways to project to an n-dimensional subspace. I take the volume of the subspace, and essentially the average of that, so up to some constant, is would be the nth intrinsic volume. So you could think of, so this gives a way of interpreting it. So it kind of this is some kind of like the average m-dimensional volume of a convex body. So this is a classic formula, Kubota. Now so another classic formula is the Crofton formula, slice formula, and this is quite often mentioned in a similar context also as Buffon's needle problem. So the idea here is that, so you can express the average intrinsic volume of a slice. So you have a certain measure on the affine Grassmannian, which is the set of all the affine hyperplanes of dimension m. And then, so you can express the integral. So again, you have a convex body. So for most of these, if the intersection is empty, this will be 0. So you're actually integrating over something that's only non-zero when there's an intersection. And in that case, so you have that the average. So if you integrate over the ith intrinsic volume of this random intersection, then you can express this in terms of an intrinsic volume of k at some constant. And one interpretation is that if you look at the 0th intrinsic volume, which is either 0 or 1, this is a special case. While the highest intrinsic volume, Bm, would be the volume, the lowest would be the Euler characteristic. Now, the Euler characteristic of a convex body, of a non-empty convex body, is 1. So this V0 acts kind of like as an indicator function. So what you have here is then, say, the measure of all E's, maybe that intersect a set K, divided by the measure of all E's that intersect a larger set B. So you could interpret this then as the probability that, say if I have a ball B, for example, and I have a convex body inside that ball, what is the probability that a affine n-dimensional space that touches B also touches K, right? And that's also a classic problem in geometric probability, and you can express this probability precisely by simply as the ratio of two of these intrinsic volumes, right? So, for example, if I don't know, if your neighbor comes to you and says, "Oh, so I would like to know the probability that say if you have a cube inside a ball and that an affine subspace of dimension m that touches the ball also intersects the cube, then you can go, oh, so I saw a talk today about how to do this, so I can compute the intrinsic volumes here, and then you can tell them the probability exactly. Okay, but in general, this is so again not very useful if you don't know what the intrinsic volumes are or how to compute them. So so one can even look at the more general problem, and this is the principal kinematic formula, which also has all kinds of generalizations into differential geometry and different areas. And so here so what you're averaging over here is you're averaging over rigid motions. So you take one, so you hold one convex body fixed, and the other one you just move it around. And then you ask, so what is the average ith intrinsic volume of that? And you can express it in terms of the intrinsic volumes of K and M, kind of and some constants that are a bit ugly, but so that doesn't matter that much. And again, it's also a special case. If you take the indicator function V0, you get a very explicit expression here, again in terms of the volumes of these two quantities, and you can then also make statements about the probability that a copy of, say, a set M that hits B also hits K, right? And so, as I mentioned before, I mean, this has been studied has been generalized in all kinds of directions and has been studied in all kinds of different contexts. Okay, but so again, so the key quantities is that we can associate these invariants to our sets, to our convex sets, that kind of tell us something about geometric probability problems involved with these. Okay, but now we have this exact formula. So the question was, since we had a result on the so before in the previous work, in the work that I mentioned at the beginning, so we were looking at a spherical analog of these intrinsic volumes, so that we work for convex cones rather than convex sets, or rather than convex bodies, and we had this concentration of measure results there. So the question that arose then at some point was, could we do something similar with these intrinsic volumes for convex bodies, which are quite different? I mean, first of all, they are not a probability distribution, they're not scale invariant, as with cones. So it doesn't matter if I of so a cone is scale invariant, but here the intrinsic volumes, they increase with scale. But is there still some way in which we could kind of get approximate versions of these kind of formulas here? So to say something like, about, for example, quantities like this. And well, so it turns out, so the theory is not as natural as in the other case, as in the Conic case, because we don't have a probability distribution to start with. Well, but we can make a probability distribution by simply normalizing them by their sum. So the sum is a quantity that's called the Wills functional. So it has made appearances in, so I think it was studied by Wills in the context of counting lattice points and there are some conjectures that relate this to the number of lattice points, so within convex bodies. But so here we consider this as kind of the total intrinsic volume, so the sum of all these partial of these intrinsic volumes. And then if we divide by it, so again we obtain a probability distribution. So for technical reasons, we use here we invert this. So we say that the probability that ik is equal to n minus I is equal to this quantity vi divided by w. And again, we can look at a summary parameter, which is the expected value of this random variable. And then it turns out that if we normalize these intrinsic volumes, then we do in fact also have a similar concentration of measure result for these. So first of all, we can say something about the variance and say, so this is bounded by 2 times the expected value here. But also the bound here, I mean, takes on this familiar form, right? So it's kind of like a Poisson concentration that we get here. And so what are the applications of this? Well, so first of all, what does this mean? So this means that typically, if I take a convex body, I will have a few of these quantities, a few of these ratios will be very small, and and they will peak somewhere in the middle. And so if we sum them up, if we sum these quantities up here, then depending on how far I sum, I will get something that's close to 1 or close to 0. Or in other words, this means that if I take a partial sum of these, the vi, then it will be already close to the complete Wills functional or close to 0, depending on how far I take this sum. Okay, so if I go farther than the expected value, or if I stop earlier than the expected value. Okay, and so it turns out that for many applications, so some of these formulas that I mentioned, like the slicing formula, so we have the projection formula, the intersection formula, some of these, they simplify, so the constants disappear if you use different normalizations of these volumes that are not intrinsic anymore because they involve the ambient dimension here. But so certain formulas simplify, and if we normalize them, so we can also, for different renormalizations, we can also obtain similar concentration results here. Okay, so this simply says that if we take these intrinsic volumes and we divide by their sum, so we get something like a probability distribution that satisfies this property. Okay, and so the key, so we're not going into details on how this is derived, but just mention what the main point here is. So if you recall before, so I mentioned the Steiner formula, which gives an expression about the neighborhood of a convex set, or the volume of a neighborhood in terms of a weighted sum of these intrinsic volumes, right? But now if you replace the indicator function of the distance being smaller than lambda by any reasonable function f, such that this integral makes sense, should be decaying, then you get kind of like a generalized form of the Steiner formula, where on this side, so you get an integral of a distance function to your convex set, and on this side you get something a bit more discrete, which is a weighted sum of these intrinsic volumes. Okay, and so maybe as a kind of exercise, well, it's not completely trivial, but it's in the case of polyhedral sets, in the sets of so polyhedra. So you can probably just I mean it's elementary to prove this identity. I mean so it's not trivial, but it's so you don't need any additional theory, right? So if you want to do this in that case, but so you can also derive this from the basic Steiner formula directly, right? So for the volume of tubular neighborhoods. But so again, so forget about these quantities here, these coefficients. So that's not important. So the only thing maybe to notice is that you have here a weighted sum where the weights are the intrinsic volumes, right? And now the idea here is that with careful choices of the function f and normalization, say if you divide both sides by the sum of these intrinsic volumes and you choose f accordingly, then so you can have on both sides on the left hand side. Oh, okay. Okay. So for a brief moment I thought that I wrote left in German here, but I said this formula links moments of a continuous. So it's not the okay. So on to moments of a discrete random variable on the right hand side. So if these are probabilities, then you can choose. If you choose f accordingly and so normalize this, then on this side you will get something like that, like the expected value of some moment generating or some kind of moment generating function. Okay. So to look at this in more detail, so if you take any random variable, there's this general strategy which is very well known. So this is by the different grammar that has the so this is very basic. So basic technique that if you have a random variable, so you can derive concentration of measure results, say bounds on the probability that this random variable exceeds t or does not exceed minus t. So based on the moment generating function or the cumulant generating function, which is this quantity here. And so now if we apply this method simply to this random variable, so to a normalization of the random variable that we assign to our convex bodies, then so all we need to get these concentration of measure results for this random variable that we want to get. So we need to find bounds on these moment generating functions and or the cumulant generating functions here. And so the way we do this is that we derive bounds for these quantities by deriving bounds for the between the derivatives, right? And yeah, I guess this I might be getting a bit technical now, so maybe I'll just gloss over this quickly. But I think so. So the main point here is that you use so you define a log concave density here, and then so you use the integral form of the Steiner formula to derive certain identities. So for the derivative of this as being equal to the expected value of this quantity with respect to this density, and the same for the second derivative. And so once you have these identities, so you want to relate them with each other, but you need a bound on this variance. So you need a bound on the variance of this function with respect to this density. And so the way you do this is, so you use some kind of a classical variant bound, so variance bounds to obtain these bounds. And so the point is, so at the end of the day, so once you do this, once you use this technology, so you get a bound for the second derivative of this in terms of the first one, and then from that you can eventually derive a bound on this quantity, and you can get the concentration result. So I'm skipping over the details, but so the point is that so the key is again making use of this formula here with some interesting choices of age to kind of relate something discrete on the right hand side to something continuous. Okay, but now suppose we have this concentration. So we know that that if we take a quantity like this here, so we divide by the total intrinsic volume, and here we have the intrinsic volume of the intersections. Now we can express each of the intrinsic volumes in here. Sorry. in the numerator, we can express this, say, as an average of, or the average of each of these intrinsic volumes here is equal to an intrinsic volume of K, but possibly shifted. So if we average the numerator here, so then the denominator doesn't change. So what we get here is more or less like the tail of this probability distribution we're looking at. And then we get kind of results like that this say that on average that the ratio here of the total intrinsic volume of a random slice to that of the original convex body, so it's either very close to 0 or very close to 1. So this means that on average the total intrinsic volume of our slice is approximately equal to that of the original body, or approximately 0, depending on so whether the dimension of the subspace that I'm intersecting with becomes large or small. And so if we plot this, then we get, for example, if we apply this to a very specific example, say if we say we take a scaled ball and we look at these ratios of the total intrinsic volumes of this ball sliced with a random affine subspace. And so as the dimension increases and as we scale the ball, then this probability will be either 0 or 1, and we have this strict boundary here. So we kind of so what we did here is we went from the Crofton formula that we originally had applied the concentration of measure of these normalized intrinsic volumes, and obtained a kind of version of that that kind of tells us that in a certain regime the probability will be very large, in another regime it will be very small. And so again, the key advantage is now that for these kind of statements we only need one parameter, right? For example, here we can deduce this to so we don't need to consider all the intrinsic volumes. So we need this one parameter here, this average, and then simply we need to know whether the dimension of our subspace, our random subspace, is smaller than or greater than this parameter. Okay. And so again, so we can derive similar results for, say, random projections, intersections of two convex bodies, and also say the Minkowski sum of one convex body and a random rotation of another one. So for example, if we look at random projections of a scaled cube, so this could be, say, like a random sonotopes in a way. So as the subspace dimension increases and the scale of the cube increases, then we get this picture here. So this means that in this area here, the total intrinsic volume of the projection will be approximately equal to, so in this area here, the total intrinsic volume of the projection will be approximately equal to that of the original body, and here it will be a lot smaller than that of the original body, and you have this kind of sharp boundary. And the same here, say, for the random intersection of two scaled balls. So if you increase the scale, so you get similar pictures. Okay. I mean, these are just examples for the computed for certain geometric objects, but the results hold in general. So the point is, so at the end of the day, so you need to know only one parameter, and then so which is this expected value of this random variable, rather than knowing all of the intrinsic volumes, and to make certain statements also about the geometric probability here. Okay, so that's it. Again, this is kind of the history of the kind of things where about this particular line of work so I've been involved in, like so this paper here in the middle with Dennis. So we had some elementary proofs in integral geometry. So the results now, some preliminary versions were derived earlier. So the main idea, I should say, or the base or the starting point was kind of investigations by Mike McCoy. And then so this work, essentially we have been having it, so we had it more or less ready for 2 years now, but due to some reasons, so we didn't quite finish it, but I'll plan to put it on the archive today. So it's now already submitted. So it's so we always try to make tweaks here and there, so it became rather large and verbose. So, but yeah, so hopefully it will be out in the next few days. Okay, so thank you so much, and that's it.